This is lesson 8.1, and it's example 5A. Now, we've gone over this problem. I want to make sure that it's very clear to everyone, and I'll also go over 5B in this video. Oh, need this open. All right. So, there was a mistake made in third hour, and I actually found out that it's because we used law of signs with an ambiguous case. As I was thinking about it after we resolved the problem in third hour, and you'll see that work in a second, I realized that our answer was the supplement of that, so we'll get to that in a minute. So example 5A, aviation. An airplane is flying with an airspeed of 475 miles per hour, so that is what we'll call vector A, and a heading of 70 degrees northeast. If an 80 mile per hour wind, we'll call that vector B, from a true heading of 120 degrees, so that's again north to east, determine the velocity and direction of the plane relative, well, it's not relative to the ground. We're just going to determine the velocity and the plane and the direction of the plane. All right. So when we set this up in third hour, anyhow, we started with our compass, north, south, east, west, and we started by drawing our initial our first one here. So here's the plane, and this is 475 miles per hour, and it's at a 70 degree from north, so this is 70 degrees, which means that this is 20 degrees because we have a right angle from north to east. I'm going to zoom in a little bit more so you can see it better because that is not very crisp. There we go. All right. Then we took our wet wind, which it says that it's an 80 mile per wind blowing from true heading of 120. So it's actually not blowing away that direction, it's blowing toward here. So if I go 120 degrees, or 90 plus 30, now here's a mistake we made 6th hour. I think we might have drawn the arrow this way. But in fact, it's from the true heading, so it's going this way. This is vector B, which we have at 80 for the side length. So there's our picture so far. Well, it's already set as tip to tail, so our resultant vector will go from here to here, and we all solved right in both hours. So if you did that right, you can fast forward to the part where we find the find this. If we had an answer of 428 for, here's our resultant vector, I'm putting it as V, the magnitude is 428. If you didn't get that in our hour or before, then watch as I go through the next steps. I'll put a big star on the page when it's time for us to move to the next explanation. So anyhow, with this picture, we're trying to find the magnitude of this. I have this triangle. This angle right here is 50 degrees. So basically, I'm just going to sketch this triangle over here. This is what I'm trying to find. And I have 475 here, and 80 here, and 50 here. So we used law of cosines. So law of cosines, we have the magnitude squared is 80 squared plus 475 squared minus 2 times 80 times 475 times cosine of 50 degrees. So we used our calculator and we put all that in. We had to make sure we were in degree mode because we've been working in radians a lot. Minus 2 by 80 by 475 times cosine of 50 degrees. And we get this value and we take the square root of it. So we get that the velocity of the plane after being affected by the wind is 427.98, so roughly 428 miles per hour. So we have our velocity, not our velocity, our miles per hour, our speed, the magnitude of the vector. So now instead of v here, I have a 428. Well, I need to know not only its magnitude, but its direction. And its direction on a north, south, east, right, in terms of true north, or true bearing. So if I come back to my original picture, it's going to go right through this angle. So let me just redraw a north, south, west, east, west line, but through this initial point on my vector. So here's my new east, north, west, south. Now, I need this angle right here. This is going to be my theta. That's part of this bigger angle right here in my triangle. Part of this bigger angle when I'm looking at this triangle. So I need to solve it. So we had the work for how we found 428. I need to solve for this angle so that I can find theta, which is this piece of it. And we'll look at how we're going to find that in just a second. Actually, we're looking at how we're going to find that right now. This angle, theta, right here, which is what I'm finding, there's our north. Right here, I have a horizontal line, and so they're parallel. And if I trace alternate interior angles, then this side length was 80, but this angle right down here is 30 degrees, which makes this angle 60 degrees. So this angle right here is 60 plus theta. Well, we've got to find that angle measure in order to find theta. So theta is going to equal whatever that angle measure is, I put it as a box, minus 60 degrees. Now, in third hour, somebody said, let's use law of sines like we had done on one of the other problems. We had an angle answer of 58 degrees. So if you were in third hour, here's what we're going to look at real quick. If you are not in third hour, you can fast forward till you see the next star. So in third hour, we got an angle answer, because we did law of sines, of 58 degrees. But that answer doesn't make much sense at all. Because if that's 58 degrees, right, then we have 180 minus 50 minus 58. That would mean that this one would be 72 degrees. That would be fine, except we forgot something when we found this angle. We forgot about the ambiguous case. And in the ambiguous case, there are 0 or 2 solutions. And in this case, there are 2 solutions. We solved the acute triangle. Law of sines would give us that. We needed the obtuse angle. That's why when I was upset that our whole angle minus 60, right, 58 minus 60 was giving us negative 2 degrees, and we said, well, that doesn't make any sense. Something's wrong. And we stopped and we went back and looked at other ways to solve the problem. We had the right setup, but we couldn't just use law of sines because we weren't thinking about the ambiguous case. In the ambiguous case, one of the possible answers is 58 degrees. The other one is 180 minus 58, which is 122. So we'll look at that in a second. That was using law of sines. Here's the star, because I'm going to show you what we could have done instead, or actually what we should have done. So when we did that, if you did that in third hour, you should have said, wait a second, my answer's not making sense. Hey, maybe there's an ambiguous case, figure out the other angle, and it would have worked out. But what we could have done, instead of using law of sines, we could have just continued using law of cosines. I could have said, hey, I want this whole angle, and I'm going to call it, let's call it angle A. So across from angle A is the 475. So using law of cosines to find the angle, I have 475 squared equals 80 squared plus 428 squared minus 2 times 80 times 428 times cosine of angle A, which this box over here is angle A. That whole angle in our triangle. So I'm going to do this part and take it away. So we got 475 squared minus the sum of 80 squared and 428 squared, which when I take that away, I get 36041 equals. When I do this, 2 times 8 times 428, I get negative 6,848 cosine of angle A. So I'm going to do, to get angle A, I need to do cosine inverse of 36041 over negative 6848. Cosine inverse of 36041, 36,041 divided by negative 6,048, close parentheses, something's wrong. Hold on. 475 squared minus 80 squared minus 428 squared. That was right. Divided by negative 2 times 8 times 428. Oh, it's not 8, it's 80. Huh, that would be why. Negative 2 times 80 times 428. It's negative 68,480. There's my error. Cosine inverse of 36,041 divided by negative 68,480. We get an angle of 121. Right, measure of angle A is is 121.76, so roughly 122 degrees, so the nearest degree. So if that's our answer for angle A, which is this whole angle, then in this picture, this entire angle, let me redraw it for you, we have this entire angle at 122 degrees. And here's north, and we know from the alternate interior angles that that was 30 and complementary that that was 60. So if this is 60 degrees right here, and my whole angle is 122, then I just have to do 122 minus 60. No, something's wrong. Is this what I did? That's right, 122 minus 60, which is 62 degrees from north. So the whole angle was 122, take away the 60, this is 62 degrees, and we can write that as 62062 degrees, or we can write it as north 62 degrees east for the direction. So that's how we get the angle for that particular problem. All right, I said I would do the other problem as well. This one's a little quicker because it doesn't need law of cosines or law of sines. We have a rowing problem. It says Jamie rows her boat due east at a speed of 20 feet per second across a river. So I'm going to start with my compass, north, south, east, west. She's heading due east at 20 feet per second. So here we go, that number, or that vector, we'll call it vector A, and that's 20 feet per second. And it's directly east. Now the other one at the same, oh, and by the way, it says toward the opposite bank. So she must have started a bank over here or whatever, and now there's a bank over here. Here's our bank. Shoreline. So now we have that the river is carrying her due south. So normally I just go due down here, but I'm going to do tip to tail because I like the triangular method. So due south at 4 feet per second. So there's B, and that's 4. And so our resultant vector is from tail to tip. Now, in all reality, it would actually be down here because it'd be pushing her down while she was rowing across. But I don't need that right now. I can just solve the picture the way it is. So we have this, and B we said was 4, and A we said was 20. And this is a right angle. So that's going to help us, because now we can just use regular trig and regular triangle methods, we don't need law of sines or law of cosines. We need to know what this is, what the absolute value over here, what the magnitude is. So I'm going to just use Pythagorean's theorem, 4 squared plus 20 squared, and take the square root to get the magnitude of the resultant vector. So 16 and 400, take the square root, is 20.39. So I'm going to write about 20 feet. It's it's a roughly 20.39 or 20.40. So I'm just going to put it down that it's roughly 20 feet per second. Not 20. That's not right. It's not 20 feet because this one's 20 feet per second. Hold on. Yeah, we'll just do 20.40 feet per second. So she's moving a little faster with the current. All right, so now we have this, and we're supposed to find the angle. Find Jamie's speed. There's her speed. And direction relative to the shore. Well, the shore is here. And here's Jamie right here. But we need it relative to the shore. So if that's the shore, then if you're standing at the shore, what's this angle right here? To find that angle, noting that these two add to 90, I first need to find this. And I can find this angle. I don't have to use law of sines or law of cosines. I can actually use tangent inverse of 40 over 20 to get it in degrees, which is 11.30, or roughly 11 degrees, which means this angle right here, our theta, from the shoreline with respect to the shoreline or the bank, 90 minus 11 is 79 degrees. This concludes examples 5A and 5B from 8.1.